I realized that the halo swapping stuff actually requires more of an introduction than I. So what I will do is I will go to the. It's on a GitHub page, so I will go to the. So let's share my screen. So this is, oh, wait a sec for it to finally appear. Right, so this is the Halo. So so what I did a while back is people, partly based on the information from that previous lecture, people were asking what happens in practice. So what I did is I wrote a simple benchmark where I set the processes up into a 3D grid, and each of them sends data up, down, left, right, forward, and backwards. And I just thought of every possible way you could do that. So so I did pairwise swapping each direction using send receive. So basically you do a send receive in every direction. So that will be 6 send receives up, down, left, right, forward, backwards. The reason why you have to use non-blocking is that if you issue the receive first, you may never get to the send. If you issue the send first, you may never get to the receive. But what you can do is do a trick where you have a 2-pass thing, and on the first pass, you split the processes into odd and even grids based on their so odd and even. It's called a checkerboard red-black algorithm. You split your grid into 2 sets, odd and even processes, and on the first pass, the odd processes send, and the even ones, well, I call it red-black here. Half the process send, half receive, and then half receive, and then half send. So that's a bit like the send receive, but slightly different. Then I did pairwise swapping each dimension in turn. So it's a bit like the send receive, but I send, a non-blocking send, a receive, and a wait. Or you can do a non-blocking receive, a send, and a wait. Or you can do non-blocking send, a non-blocking receive, and a wait. But this is all in order. Then the thing which I said should be the best, non-blocking comes in all dimensions directions at once. So you issue 6 I receives, 6 I sends, and you just do a wait all. I did the same thing with persistent communications, and I also did neighborhood collectives. I haven't covered them here, but neighborhood collectives are basically a way of doing. You could neighborhood collectives allow you to do halo swapping with a single call. So there's a routine called MPI all-to-all, where you communicate, every process communicates with every other one. That's not what we want, because we don't want every process to communicate with every other. We want every process to communicate with the 6 nearest neighboring processes. MPI neighbor all-to-all does that. It says communicate with all your neighbors, where the neighbors are your 6 nearest neighbors, up, down, left, right. I haven't had a chance to cover that yet, but again, so this is what it does. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9 different. Is that 9? 9 ways of doing halo swapping. And if you look at the, for example, the actual code. Now it's written in Fortran. I normally apologize for being in Fortran, but then I shouldn't really, because half of you are Fortran programmers, so I won't apologize. I actually have no objection to Fortran at all, although my Fortran may be a bit rubbish. The way I do it, there's a driver routine, but it really does do something fairly simple. Let's look at the send receive. Yeah, halo send receive. So this says do halo swap with this number of repetitions. This is the send buff. This is the receive buff. This is the number of elements. And CartCom, I arranged the processes in a 3D grid using Cartesian communicators. And so this com data call basically just extracts all the information to your neighbors after the communicator. It's just a setup routine. But then I do something very, very simple. do IREP equals 1 to NREP. We do a number of repetitions because we have to do lots of if we did a single halo swap, it wouldn't take enough time, so we have to do lots of them. I loop over the dimensions, which is X, Y, Z. I loop over the directions, which is up and down, and I basically do a send receive, and there's a bit of jiggery pokery here. But basically it's looping over a number of repetitions. So this is doing explicitly 1,000, I think about 1,000 times, we'll see how many, but NDIM is 3, NDIR is 2 up and down. So we're doing 12 calls, we're doing 6 calls to send receive. Okay. But that is doing them, these complete immediately, they're completing in terms, we're doing an ordering, up, down, left, right, forward, backwards. If you look at the halo, I send, I receive, wait, all here, this basically loops over the dimensions, the directions. I have a request here. This is send and receive. This is looping over send and receive. This is looping over 3 dimensions. This is looping over the 3 dimensions. This is looping over up and down, and it calls it either calls an I receive or an I send, depending on what loop we are, and then it just does a wait all at the end. And the driver routine is very simple. It's called halo bench, or you can specify the size of the buffer. We're transmitting 10,000 doubles here, so that's 80 kilobytes roughly. We're doing it for 1,000 times. Max run is I run the whole benchmark 3 times because there can be a warm up. So the first time you do this, you may not get reliable results. So I actually run the whole thing. This is a recent addition. I run it 3 times. But hopefully, as you should just be able to run out of the box and get sensible results. So if we basically just so the instructions hopefully are so download the code there to ARCHER2 doing that, and then so let's just check this works. I'll have to submit a different job, share a different screen. Oh, I've lost my, okay. Have I? That's weird. Didn't seem to want to pick the, there we go. So wait for a second that to appear. Okay, so let's go up one. So I'm in my, we clone the halo bench. Oh, well, I've already done it, but I did it, use it as this for, okay. Git clone, cd halo bench, make -f make file ARCHER2. There are some warnings because my Fortran isn't particularly good. I've included the same module twice in some tree it's complaining about. And then I would like to run in the reservation. So I will edit the code. Sorry. I wanted to use the that reservation there, VS batch. So by default, what it's doing is it's running on 8 nodes with 128 tasks per node. So we're running on 1,024 processes in a 3D grid. Let's see if are we running yet. I'm running, yeah. So there's only 8 nodes in the reservation. So if you use the reservation, you'll have to queue up a bit. But it runs for longer than I remember because it's doing it's completing that, because it runs the benchmark 3 times. But if we look at the output, Well, so that should work. So it does seem to work. So if people want to run that and have a look at the results, you should see quite a clear hierarchy of which the best. So it prints out for each method, it prints out the bandwidth. So actually, it prints out. Oops. For each method, send, receive, read, black, it prints out the how long it took, and it prints out the bandwidth. But it runs it multiple times. So you probably want to look at the final one to get the best answers. But try running that. The things you can alter are that buffer size is probably within the eager limit. You can make it larger. If you make you have to manually alter the number of repetitions. So if you make the buffer size bigger, you have to make the number of repetitions smaller to keep the runtime sensible. As I said, that's in Halo Bench.f. Just right at the top, I've got buffers. They're doubles. So that's 10,000 doubles, and I'm running each one 1,000 times. If you make this 10 times bigger, you probably want to make that 10 times smaller. You want to keep the runtime within about a second. Something like a second is a sensible number. So I'll just let people, if you have any problems, that did seem to run out of the box. So you won't be able to, but I can. Does Git not work? So you should be able to just cut and paste the Git command from the website, but you will be able to, if we go to well, you can actually so you should be able to copy it from there. You should be able to copy it from work tier 226 shared. So that you don't have access to my home, but you should have access to that directory. Okay. Well, okay. I see what you mean. Yes, I see what you mean. I keep forgetting. No, well, for me, I didn't need to. This is a completely fresh account for me, so I was able to get it. But you should be able to. You can't. So the permissions are quite strict on ARCHER2. You can't copy from people's directories. But I've checked out a copy in. This you definitely can read from. You shouldn't have to configure Git. Well, maybe I'm being oversimplistic, but that you should be able to copy from. That work tier shared should be accessible. Individual user directories are quite strictly permissioned. Yeah, you should just be able to do it. I am very naive. You should just be able to. I'm using a vanilla account here. This is just straight out the box. I just did git clone blah and it worked for me. But if that doesn't work, you should be able to copy from that work TA20626 shared. That should work for you. So I didn't used to have that warm-up phase, but we discovered recently that one of UCX or OFI has quite a high startup cost. I mean, high as in a few seconds. You wouldn't notice it in a real program, but the first time you do a send, receive, or something, it does some setup. So I have that warm-up. I did it for 3 times. The first to warm up, the second is supposed to be real, and the third is supposed to check the second one was reliable. So let people just play around with that. And if you want to run on more than 8 nodes, you can, but you can't run in the reservation. The reservation is only 8 nodes. You can run in the normal short queue, which allows you to run on up to, I think, 32 nodes. I might be wrong. So I'll just I'll be. I'm a bit dehydrated. So I will be gone for 2 minutes if I get some, and then I will maybe come back. If people can, have people been able to run? Yeah, fine, good. So I'll let you play around with a few things if you want. I'll take a 5-minute break. I just need some more water. I seem to be quite dehydrated today. But I will just be back in 5 minutes, then we can discuss the results. Um, so it looks like people will be able to run. If you're running the reservation, you would have to. So if you're running on 8 nodes, there are only 8 nodes in the reservation, so you will have to queue up for other people. But let's have a look at some of the numbers here. So if we look at the so you'll see that it says in running 1,024 processes, it arranges them in a grid, which is 16 by 8 by 8. Each halo contains 1,000 doubles. Total amount of data is 0.5 megabyte per process because we have 6 halos. So we have about 80 megabytes times 6, 500, 150 megabytes of data. And the block resolution. I will go to the bottom because I think the third run should be the most reliable. Bedroom on 3. So we'll see here that, yeah. So send receive was 670 megabytes per second. Surprisingly, the red black was, which has a bit more logic, it was faster, but send receive are all very much for muchness. In fact, There's nothing magic about send receive. If you downloaded, so send receive. So the problem about halo swap, you do a send and a receive, is you did send first, you may block and never get to receive. If you do receive first, you may block and never get to the send. Send receive is a routine I don't really like, but it basically does the send and the receive at the same time. However, if you looked at it, it'll just do an I send and an I receive, no wait, no doubt. And you can see that, not surprisingly, actually it looks like I receive, right? It's almost identical to my guess here is doing I receive, send, wait, for example, probably. I mean, look at that's remarkably similar. 669.5, 669.4. I mean, but these are all the 670. But then we get onto the anything you do. So anything where you impose an order, where you do the dimensions in order, you get a much slower so you get much slower than if you do something where you do them all at once. So I receive, I send, wait all gets go over a gigabyte per second aggregate, and it's almost identical. The persistent is the same, and the neighborhood collective is the same. So these are all basically the same thing. You do non-blocking in every direction, and then you do a wait all, and so we're getting quite significant increase from like 670 up to 108. That's quite significant improvement. Was it worth doing the repetitions? Well, if you look on the first run, send receive is anomalously slow. It looks bad, but that's just because it's the first routine that's run. And so if we look at the run 2, hopefully, yeah, we're back up here. So that I didn't used to have this run an event, but it does seem to, yeah, that does seem to. And the reason is, you know, you're sitting there doing halo swapping up, down, left, right, okay. You might say, right, I'm waiting for I'm going to wait for a message from the guy up the way. That person could be on a different node going over the network, whereas the communication from the neighbor to the left could be on the same node. It could be coming in really quickly. That's why you don't know what order these are going to come in, because some of them are coming from off node, some of them are coming from on node. And so, you know, that's why prescribing an order, I will do the communications up, down, left, right, forwards, backwards is a bad thing to do, because the time taken to do those communications will vary vastly depending on a whole number of factors, even as simple as whether your neighbor is on the same node or on a different node. We could try trying, you know, a larger, well, and see if there's any difference here. This is doing a much larger, a much larger message, but fewer repetitions. So I think this is above the eager limit, which is why it's taking a lot longer. Is it running at all? It's running at the moment. I don't know how far. Is it finished? Yes. So you can see that if we go to the end, the third one, yeah, we're getting similar results. Oh, the red blank here, it's interesting. You wouldn't, but these are all at the 500 megabytes. But yeah, we're up to the. So again, you know, these things win out by quite a lot. And then we can maybe try again. We could do, whoops. We could do the opposite. Sorry, I'm being a bit derpy here. It's the end of a long day. We could change it to be smaller. Oh. 10338236 So you just watch them as they come out. So again, it's only 5,600 and yeah, 7. So this is some similar picture. So the red black comes and goes, but the other ones are all very good. So the results are all very different, but I mean we're getting and you can see the bandwidth there, as I said, it's more like a gigabyte a second, not 10 gigabytes a second, because you're having lots of processes going down the same network links. You can play some. Well, I'll do one final trick, which we could do. What am I trying to do? What we could do is we could try and say where our Halo swap, where our ping pong results reliable. Well, I could do one task per node. Okay, so I can basically say here I'm doing Halo swapping between. I'm doing this benchmark, but I'm doing it in a way where we're not sharing a network connection. We have 8 nodes and we have one task per node. Okay, so we would expect that. Let's go back to the default, which was that. Just. Is that right? Okay, yes, it is. Yeah. So yes, you're seeing we're getting the bandwidth is now 5 gigabytes per second. Now we measured 10 with the ping pong, but remember the ping pong is unidirectional. Here we've got bidirectional. So my guess would be each process is getting 5 gigabytes per second, but the network is sustaining 10. My guess being that you're doing bidirectional comms, whereas ping pong is not. Ping pong is one way than the other. So you can see that the fact that we're getting a gigabyte per second, not 10, or is due to the effect. So you can, if we arrange the processes as one per node, which is more like the benchmark run 2. Okay, they're all much for muchness here. So again, this is interesting. Okay, this shows. Okay, this is very interesting. Okay, not only is the bandwidth much higher, the difference between the send receive, for example, and the persistent, and this is that's because this is sort of a load balance calculation. Every process is doing the same thing. Every direction is on the network. So they're all very symmetrical here. So this idea of, so I suspect the reason that they're all similar here is we're not getting this load balance, or all the communications taking up at roughly the same time. So it doesn't matter if you order them. That's my guess. But I might be wrong. But that you can play around with these things. It's quite interesting. So okay, that was really all I had to say. I have a hard cutoff at 4, unfortunately. As I said, I've slightly messed up on the timing here, but the crux. I'll stop sharing that there. The crux of the collectives lecture, advanced collection, is that things like gather and scatter look nice. If you remember, so scatter takes a data set and splits it up into lots of sections. So if you have a large vector and you want to send a portion of it to every other process, which is something you might want to do at the start of a calculation, you read it in on one process, and you want to, that's fine. You just do an MPI scatter and you send a little section to each data, to each other process. That does not generalize to 2D for a whole bunch of reasons, because a 2D decomposition, it's just more complicated. So at first sight, it looks like, oh, I can't do scatter and gather for distributing and collecting a 2D data set distributed across 2 dimensions. It turns out you can, but you have to play around with MPI data types. And the trick is you have to do something, it's explained in the lecture, you have to do something called MPI type resized. Basically, you have to basically, when you do sends and receives in MPI, you don't specify, you specify count. You say send 1 of these, send 2 of these, for example. And so, and that is automatically multiplied up by the size of the object. That's clear how big an integer is or a double is, but when an object is a subarray or a vector where it has gaps in it, it's not really clear how big it is. And it turns out that MPI's definition of how big a vector is not particularly useful. So you have to do a rather nasty thing called MPI type create resized and tell MPI, look, I know you think this vector, this subarray is this size, but I want you to think of it as being this size, and then you can do various tricks. And so it's a bit technical. Hopefully it's explained in the lecture, and there are solutions there you could look at. But the main thing is it's basically saying that it is possible to use things like scatter and gather for doing distribution and collection of something like a matrix decomposed across both its dimensions, but you have to understand what you're doing, and it takes a bit of jiggery-pokery, but it is worth doing because collectives will be so much more efficient than doing it by hand. And I'll just double check that. If you look, there is a exercises on the GitHub page. There is well, I've got collected tar, but there is the directory, and you will see this. So merge. So this is to do with user-defined reductions, which I'm not going to cover here. But for example, MPI gather.c, MPI gather2d.c. These are all explained in the lectures, and it explains what it's trying to do here. Okay. So this is so the exercise is explained in the comments at the top, which is maybe not particularly MPI gather2d, so it says here. The exercise, okay, so we have a matrix distributed like this across this process grid. Use a combination of MPI gather and the resource vector to reset this in the correct order to rank 0. So here we're doing a gather. So I initialize the matrix like this. I want you to pull it back together so we have the correct layout on. And it's slightly confusing, but there is a solution there. MPI gather2d solve.c, which does this by doing a deceptively simple gather, this MPI gather v here, but it requires a bit of jiggery-pokery with this resize vector, which is this MPI type create resized. It's explained in the lectures, but it's a useful. It's basically telling you. It looks like this pattern is hard, can't be done with gather and scatter, but it can, but it requires fairly in-depth knowledge of data types. And it's a bit technical, but it's explained in the lecture. You can look at it, and I'm happy to go over it if you want, but there are solutions there showing you how to do it. So I'm sorry I got my timing slightly awry, but I think that's probably that's it, that you can use gather and scatter for more complicated patterns than just one DD composition with associated with trickery with data types. So I have to go now, apologies, but we'll start up again tomorrow, and tomorrow is focusing on using shared memory within MPI, and there are 2 ways of doing that. One is hybrid MPI OpenMP, and the other is to use explicit MPI has its own shared arrays, which are a bit like OpenMP shared arrays, and I'll cover those tomorrow. So we'll start again at 10 o'clock tomorrow, and hopefully the timing will go a bit better tomorrow because it's more like the one I've done before. But okay, so see you tomorrow.
Thank you very much.